Good afternoon.
Hello.
Hi.
You excited for Clone Wars?
Oh, I am. I am. I was glad to the. Yeah, there's several people asking me. Okay. Uh, the last few episodes have been. It seems slow at first, but because the Echo. I mean, yeah, the Echo storyline didn't seem super important. Uh,
Yeah.
but these last few episodes are really cool. Uh, and it was cool that the most recent episode on Friday you could see in what was happening that the siege of Mandalore, like that episode plus the next few, are taking place concurrently with episode 3.
Yeah. I'm thinking they're gonna reuse John Williams soundtrack for that final episode.
Oh, I hope so. Yeah.
Yeah.
When it seems close enough that at the very end of the last episode, they could possibly even reference Order 66.
Didn't they kind of already with that part with Ahsoka? I thought
So,
they did. I thought there was a part, maybe it was a preview. I forget. I'm not completely caught up. I'm one episode away.
oh, okay.
But she
Well, this past episode that I guess you haven't watched yet, um, a lot of information happened. If you're one episode behind, the most recent episode you watched, the very end of it, she was planning with those Mandalorians to go to save Mandalore and stop Maul. Um, but in the most recent episode, you see even more uh, like her beginning to take the fight to them, and based on some other information that's given in that episode, you can tell that it's concurrently with the beginning of episode 3.
Mhm. Okay, that makes more sense.
And I say that because there's a point in the most recent Clone Wars episode that um, Obi-Wan and Anakin and most of their battalion, they,
Going to Grievous.
yeah, they're not able to go help Ahsoka against Mandalore. I mean, against Maul, because they had just gotten word that um, that Grievous is attacking Coruscant and has taken the Chancellor captive. And so when they split ways, I mean, that's pretty much the beginning of episode 3. So the last few episodes are all happening while episode 3 is happening.
Clone Wars.
Yeah.
Did you like the first episode?
The first episode of Clone Wars?
The last arc.
Uh, wait, what? What was your question?
Just the first episode they have for Siege of Mandalore, like last Friday.
I thought it was good. I thought it was they gave a lot of good cool information about like it's the timing, and it was fun to watch. Yeah.
Did you like the memes?
The what?
The memes.
I did. Like I wasn't sure if people were actually going to do it, and then I saw that. I don't know who actually made the folder or how many of y'all actually put the memes in there or whatnot, but it was pretty cool. Thank you. Okay. Oh, which one was my favorite? Um, I've seen a lot of generic math memes, so I think in the ones that y'all posted, my favorite ones were the ones that were like more specific to our class, like it, because because then it referenced a memory. Or I thought the one with SpongeBob's expression, Mr. Hunter, when someone doesn't understand the concept, I thought that was kind of funny. Both your coronavirus ones were pretty funny. And then the other SpongeBob one with the inverse trig integrals and derivatives, and SpongeBob just putting that up. Thought that was pretty funny. Okay, oh, Jessica's. Okay. Well, it's 1:05. Like usual, we'll start now, but I'll admit the others as they join in. It is being recorded like usual. 11 out of 20 of you, that's a good percentage, much better than AB earlier today. Okay, well, let's start off with the same information as before. Oh, this is going right to the memes. Oops. Let's go. Yeah, here we go. So again, apcoronavirusupdates.collegeboard.org. That's where you can get a lot of the information, really all of the information about any of the changes to this year's exam. Within the next week or two, really soon, don't know exactly when, you should also be notified of it, I'm sure. They will be coming out with tutorial videos and a lot of information about how their online system will work during the exam. And I think they may also like allow like a trial or tutorial practice run on that in using their system ahead of time. So I don't have that specifically. I know it's not up right now, but there will be a chance before the exam either for you to at least watch tutorial videos of how that system will work, or actually practice using it. Then your exam is May 12th at 1 p.m. Or if something happens there and that doesn't work, make up on June 1st at 3. So, well, May 12th, that is 3 weeks from yesterday. So less than 3 weeks, 20 days until your exam, until the AP exam. It again is online, 45-ish minutes for your response to questions. The first question will be 25 minutes, 5-minute upload time, 60% of the exam. The other one, 15 minutes, 5-minute upload time, 40% of the exam. Because of the scenario, it is open note, open book, calculator allowed but not required kind of exam. And speaking of the calculator aspect, I may post the link later today or something, but I mentioned this to AB as well, that the TI has made their TI-84 software, like emulator software, available for free to anyone right now because of the exam. Because I mean because of the coronavirus, they're aware students don't have access to their normal school calculators. So if you don't have your own TI-84, you could download the TI-84 software from TI for free right now, and that would definitely help you for the AP exam. Okay, well, talking about differential equations. A differential equation is any equation involving a function and its derivatives. Any equation involving a function and its derivatives. Normally how we would see it is you'd be given something of prime of x equals or y prime equals or dy dx equals. So this is on the humongous differential equation, the humongous review sheet, unit 7. Number 2 is talking about slope fields. You need to be able to draw one. You need to be able to draw a solution curve. Or if you're given a slope field, identify the differential equation or identify a possible solution equation. All of those are things you need to be able to do with slope fields, although most of you found slope fields rather easy, so don't have to worry about that. Number 3, Euler's method. Okay, let's purple. So on Euler's method is essentially using a bunch of consecutive tangent lines over and over and over again, splitting up the steps based off the differential equation to be able to find some new point. Purpose is to estimate some new value. So what we did before, we made a table. At x, we had y. We had a column for dy dx. We also had a column for dy. I mean, that column wasn't super necessary, but definitely helpful. Problems that require Euler's method will always tell you what the step size is, and the step size is the change in x each time. Change in x each time. So your delta x, that is the step size, which would be given in an Euler's method problem. And the dy for this last column, well, that's going to be the change in x step size times the dy dx for that particular step. And then to figure out some new y value, the nth y value, we just take our previous y value and add the dy. And we'll see an example of Euler's method in a little bit, because I'm going to do question 4 on the 2016 free response questions. I'll do question 4 on the 2016 exam. And then number 4 says, what's a separable differential equation? Well, it's one where all the x terms and y terms can be separate. So you have a differential equation dy dx equals something, and the x's and y's have the ability to be separated such that you could then move anything dealing with y over to one side and anything dealing with x over to the other side. And that is always the first step in solving a separable differential equation problem. So step 1, you would separate the variables, and you need to show that step. Step 2, you would then integrate with having a plus c. You gotta have the plus c. Cannot forget the plus c. Whether it's an initial condition problem or not an initial condition problem. And then you would solve for y. And that's the only 3 steps you would do if you're just asked for a general solution. That's all you would do if you're just asked for a general solution. If you're asked for a particular solution, like question 5 is talking about, the easiest way to do it then is right between steps 2 and 3, right after you integrate, then you would plug in initial condition and solve for C. Do it right there. That's the easiest, most accurate way to do that. Plug in your initial condition and solve for C right after you integrate. Then once you figure out C, you'll plug it back in to get to then be able to solve for y. Oops, I don't want to go that far. Okay, so then question 5, describe initial condition or particular solution. So again, right after you plug in the initial condition, right after integrating to find C. That's the only difference in solving one with an initial condition. 6, write an exponential differential equation and give its solution. So dp dt equals kp. That's an exponential differential equation, and I call it that's an exponential differential equation because when we solve it, we get an exponential equation as a solution. So, and I just showed all the steps here that we would first divide both sides by p, multiply by dt by dt. That separates the variables. Then we integrate, and you e both sides. When you e natural log of p, it just becomes p e to the c. Well, that we could just call that a c down in front. And really, when time equals 0, c is that initial population. So we could just replace c with p sub 0. And then 7 is talking about logistic functions. So talk about that for a little bit. And if you've been paying attention to the news and all the graphs dealing with coronavirus, you should really be recognizing the logistic function that we talked about back then, since that's essentially what the virus is. Usually the graph that they show that they're talking about flattening its curve, that's the original. That's the differential graph, not the original function, though. Okay, so a logistic differential equation. One version of it looks like dp dt equals kp times 1 minus p over m. Or the other version of that is that dp dt equals kp times m minus p. Now, there's always different ways to write these. Sometimes people will have y instead of p. Sometimes they will have l instead of m. But it's the same general idea. Where my p, it's the dependent variable, represents the population of something that's occurring in a differential way. T is time. K is just some random constant that ends up happening. And m is the carrying capacity. M is the carrying capacity such that the limit as p approaches infinity of p of t equals m, such that the limit as t approaches infinity of p of t equals m. And to remind ourselves of this graph, that y value could be m over 2 there, between, I should adjust that real quick. I'll just do that. There we go. Yeah. Before the population, the y value here is the population. It's like how many people, I guess maybe you would say, have the virus, or really have had the virus at any time. And then after n over 2, that's the point of inflection, and it starts approaching that. Okay. The solutions would be p Solution to this version is m over 1 plus c e to the negative kt. 1 plus c e to the negative kt. Solution to this version is p over m. P equals m over 1 plus c e to the negative m kt. Okay, fastest possible growth occurs at the point of inflection. So, fastest growth would be at the POI. So when the population equals m over 2. In a logistic equation and scenario, it will be concave up anytime the second derivative is positive, which will be when p is between 0 and m over 2. And it will be concave down anytime the second derivative is negative, which is when p is between m and m over 2. Okay. And the most common thing you could have to do with a logistic differential equation is talk about concavity, talk about the point of inflection, like say when it is, when it would be concave up, concave down, say when the point of inflection would be, or say what the carrying capacity is, and those kind of things. They definitely not this year would ask you to actually solve. That they wouldn't ask you to solve for the solution. They wouldn't ask that because if they want you to solve for that solution, there's so much in that, and that's just such a time waster. They could ask some of those same concepts in some other problem. Okay, so that is unit 7. Talk about unit 8 a little bit. Well, mean value theorem, for integrals, and average value theorem, those are almost the same thing. Almost the same thing. And I'll just talk about them both at once by talking about the mean value theorem for integrals, which says that if f of x is continuous on an interval from a to b, then there is a c in AB where f of c would equal the average function value, which is the integral from a, nope. Missing one very important part of that. The average value is where we take the integral and divide by the width of the integral. Take the integral over the interval and divide by the width of the interval, meaning 1 over b minus a in front times integral from a to b of f of x d x. So I answered both 1 and 2 in this one thing where that whole section there, that's the formula for average value of a function. The integral from a to b of f of x dx times 1 over b minus a, that gives you the average y value of a function, or average function value over an interval. And just the mean value theorem for integrals says that if a function is continuous on an interval, there is for sure going to be some x value that would give that y value. And that's all the mean value theorem for integrals really says. That after you find the average y value, if it's continuous, some x value will produce that y value. Number 3. 3 is asking for total displacement. Displacement can be the integral from a to b of velocity. Integral from a to b of velocity. Because then if we took the integral of velocity, we would get position, x of t. And then we'd have our little bracket from a to b, and then we'd plug in the upper limit and subtract plug in the lower limit. So that would also be x of b minus x of a. That's displacement. Distance. The integral from a to b of the absolute value of velocity. Integral from a to b of the absolute value of the velocity. 5 and 6 are asking for the formula for area between a curve and the x-axis in terms of x or in terms of y. Well, area between a curve and the x-axis, well, that just means area under a curve. And that should automatically make us think of just a definite integral. So, I mean, that shouldn't be hard to figure out. So 5 was super easy. Should have already had that one in. But the difference in 5 and 6 is 6 asking formula, distance between a curve and the y-axis in terms of y. It's like in 5, a and b are x values. I could say that x equals a and x equals b. In 6, a and b are y values between y equals a and y equals b of f of y dy. Okay, next page. Well, next page in the slides. Same page on the paper. 7. Formula area between two curves. Okay, well, if we want between two curves in terms of x, so we're going to go from a to b. If we're in terms of x, a and b are x values of f of x minus, call the other one g of x dx. And how we said this in words before was that would be top function minus the bottom. Then area between two curves in terms of y, that'd be from y equals a to y equals b of f of y minus g of y dy. And when it's in terms of y, that is the right function minus the left function. And number 9, formula for volume of a solid with cross sections. And then based on these given bases. In general, volume would be the integral from a to b of a of x dx, where a of x represents a function for the area of whatever you're dealing with, where a of x represents the function of each the area of each cross section. So then, if all we're thinking of is the region, if the base is just the region bounded by the function and the x-axis, bounded by the function and the x-axis, then for squares, our volume is the integral from a to b of f of x. You know what, since I'm going to do this, f of x minus 0 squared dx. I did that to say that we want our area, this a of x, what's going to go here, to represent what the area of one cross section would be. So I have my f of x is my top function, minus 0 my bottom function, top minus bottom. Well, the top minus the bottom, well, that then gives me the side length of the square. Well, a square is side squared. Similarly, the volume for semicircles, we get a volume equals integral from a to b. Actually, I'm going to put my coefficient out front. So I'm going to put my pi over 2 out front because it's a semicircle. So for a semicircle, the area of a semicircle in general is pi r squared divided by 2. Pi r squared divided by 2. And here's my pi over 2 part. So I need the rest of this to be the r squared part. Well, the distance between the top function and the bottom function, I'm just going to write it like that. I'm just going to write top minus bottom. Top minus, that way, very generic formula. Top minus bottom, that would give you the diameter of the semicircle. Top function minus the bottom function will give you the diameter of the semicircle. Divide that by 2, then that's the radius of the semicircle. Squared dx. And so that would end up being the formula for your semicircles. And then for equilateral triangles, we'll do it the same way. A formula for an equilateral triangle in general is, the side times root 3 over 4. Side length times root 3 over 4, that's the formula for area of an equilateral triangle. So I'm going to put that root 3 over 4 out front, integral from a to b. Then I want this to just, wait, I should have side squared. That's side squared. Side squared, root 3 over 4. So I need this to represent the side squared. Well, that side length is just going to be the top function minus the bottom function. Okay. But equilateral triangles, that's really where squares and semicircles are the most common, or rectangles, where they very specifically give you how to get the area. Sometimes I've seen previous ones questions where it's rectangles and they'll tell you like the height is 2 times the base, or the height is the base minus 3, something like that. So rectangles, squares, and semicircles are the most common. Disk method. Okay. Disk method, the volume is going to be pi. Well, this method, it's essentially adding up infinitely many circles as the width, like disks, as the width of the disk approaches 0, and as the number of disks approaches infinity. So we're adding a bunch of circles, which is the area of the circles, pi r squared. So it would need to be pi. That's going to be there for all of them because that's just a coefficient. Well, r changes depending on like where you are in the function. So that's going to be part of your equation. So r of x squared dx. And then washer method. Well, that's going to be maybe something like something like that rotated around the x-axis. If that is rotating around the x-axis, well, then you got this missing section in the middle. You got that missing section in the middle, so you're going to end up with a big radius and a small radius. So our volume here is going to be pi. I should have an a to b there. Integral from a to b of capital R squared minus lowercase r squared. I mean, and really there would be a dx, and both capital R and lowercase r, they're functions of x. Or it could be rotated around this. They're functions of x if it is around a horizontal line. Functions of x if it's around a horizontal line, and if it's around a vertical line, it would be functions of y. If it's around a vertical line, it would be functions of y. And last thing is the equation for arc length. Well, in arc length, L equals the integral from a to b square root of 1 plus f prime of x squared dx. And we used that last time when I showed one of those problems from that free response question. Okay, well, only one person ahead of time told me any free response questions they wanted me to go over. So Isaac asked about from BC number 2, letter part D. So I will definitely go over that. And since no one else asked any, I thought it'd be good to go over number 4 on the 2016 because it covers a lot of different things. So we're going to do that first. Number 4 on the 2016 exam. So this is from the 2016 response questions, number 4. And then after this one, I'll go over some of the BC2 that Isaac asked about, or if anybody else has any other questions from the free response questions for this week. Okay, so 2016 free response questions, number 4. Oh, by the way, everyone, every year, 2 questions on the AB free response are the same as 2 questions on the BC. And in 2016, the 2 questions that were the same were numbers 1 and 3. And I went over question 3 from the 2016 exam with AB last Friday. So if you have any questions about the number 3 from 2016, you could just check Friday's AB video. You could check Friday's AB video, and that would help you with number 3. And then we're going to go over number 4 right now. So first thing we're asked to do is get the second derivative in terms of x and y. Get the second derivative in terms of x and y. So that's going to require some implicit differentiation. So first part A. Okay. We're just going to take the derivative of each term with respect to x, and if it has a y in it, then we've got to do chain rule, and it'll also get multiplied by that derivative as well. So the second derivative of y with respect to x. Well, first, we got derivative of x squared is going to be 2x, then minus 1/2 times. So derivative of negative 1/2 y would be negative 1/2 times the derivative of y. So it will be minus 1/2 dy dx. Okay, now that right there, that is not good enough. That would have given you just 1 point on the AP exam that year. Remember, things are out of 9 points, and since we're going over an actual free response section of an AP exam, I can tell you how much each thing was worth. So now, since they said they wanted the derivative in terms of x and y, we're going to replace dy dx with what dy dx equals. So we have 2x minus 1/2 parentheses x squared minus 1/2 y. And that would be our answer. So that now this entire section is worth all of letter A was worth 2 points. Okay, next, part B. I'm gonna box that in real quick because we're going to use that later. I want to easily find it. Okay, part B, we're told let y equals f of x be a particular solution to the given differential equation whose graph passes through the point -2, 8. Whose graph passes through the point -2, 8. Does the graph have a minimum or a maximum or neither? Okay, so we want to know at -2, 8, is that a min, max, or neither? Okay, well, we have the first derivative, they gave that to us, and we have the second derivative. So let's just figure out what those are at that point. So dy dx at -2, 8. Well, that's going to mean -2 squared minus 1/2 times 8. Well, -2 squared is a positive 4. 1/2 times 8 is 4, so that would end up being 4 minus 4, which is 0. Okay, so it could be a minimum or a maximum because the first derivative of -2, 8 is 0. Let's now figure out the second derivative of -2, 8. Squared 1 x squared at -2. So we're going to plug -2, 8 into the second derivative that we found earlier, which would be 2 times -2 minus 1/2 times -2 squared minus 1/2 times 8. Well, this entire parentheses section over here, well, that is the first derivative. So we already know this section here is 0. So this is 2 times -2 minus 0. So this whole thing is -4. Okay, well, that means that our first derivative of -2, 8 is 0. Okay, so we have a horizontal tangent there. Our second derivative at -2, 8. So this implies horizontal tangent. Now our second derivative of -2, 8 is -4, meaning concave down. Okay, so it's horizontal tangent and concave down. That means by second derivative test, -2, 8 would be a what? Would it be a min, max, or neither?
Max.
Yep, it would be a max. Okay. And that entire part B was worth 2 points. Worth 2 points. So it was worth 1 point for the answer that it was a relative max, and then 1 point for having correct justification. And really, in the actual scoring guidelines online, they did not include the term second derivative test. So that does not actually need to be there. As long as you say that the first derivative is 0 and that the second derivative is -4, those two things together imply that it is a relative maximum. So you don't even really need the term second derivative test, even though that's what we're doing. Okay, look at part C and D. Part C. Okay. Part C, well, we got this y equals g of x is another particular solution with the initial condition g of -1 is 2. We're asked to find the limit as x approaches -1 of g of x minus 2 over 3 times x plus 1 squared. Wow, okay. Gotta show all of our work too. Well, this is probably gonna involve L'Hopital's rule, and let's show that. So for part C, limit as x approaches -1 of g of x minus 2. Well, that right there, g of -1 we were told is 2, so that equals 0. And the limit, if we look at the bottom, limit as x approaches -1 of 3 times x plus 1 squared. Well, that would also equal 0. Okay, so we can use L'Hopital's rule. So we have the limit as x approaches -1 of g of x minus 2 over 3 times x plus 1 squared. By L'Hopital's rule, that's why I have my LH. I found out recently writing the LH is actually, not absolutely required. Not absolutely required. Showing that the limit of the top equals 0 and that the limit of the bottom equals 0, that is in some way. So you can either do arrow that the top approaches 0, that's how we did it in class, and that the bottom approaches 0, showing that they individually approach 0, then setting it equal to the limit. Got to keep your limit notation. That is required. Just the LH isn't. So doing L'Hopital's rule is what's necessary, but you don't have to actually say that that's what you're doing, is what I recently found out. So now we take the derivative of the top and derivative of the bottom. Derivative of the top would now be g prime of x. Derivative of the bottom, well, 2 will go in front. That's then 6 times x plus 1. Okay. Well, can we now get that limit? But if I was to take this limit, that bottom also goes to 0. And g prime of -1, we could figure that out real quick. If dy dx at the point -1, 2, well, that would be -1 squared minus 1/2 times 2. Well, that also is 0. So the top also goes to 0. Okay, got to do L'Hopital's rule again. Equals, I'm still going to put the LH. Doing L'Hopital's rule again. Now limit as x approaches -1. Okay, second derivative at the top. So g double prime of x over. Derivative at the bottom is now just 6. Okay. Now we just need the second derivative of of x at this point? Well, that would go back to what we wrote down previously. What did we have as the second derivative? The second derivative of y with respect to x. We had two. Right. What is going on? Two x minus 1/2 times well, dy dx. I'm just doing that like that because we already know that dy dx at the point is 0. So that section's 0. That's really just going to be the 2x. It's really just going to be the 2x. And so we can evaluate that. That would just be 2 times -1 over 6 or -1/3. There we go. That's part C. And now part D. Part D is telling us h of x is going to be a particular solution to a given differential equation where h of 0 is 2. Where h of 0 is 2. We're asked to use Euler's method starting at x equals 0 with just 2 steps of equal size to get h of 1. We want to approximate h of 1, and we just have 2 steps of equal size. So we're going from h of 0 to h of 1. So for part D, I'm going to section this off real quick. Everything else will be for part D. For part D, our delta x is, well, we're going from x equals 0 until x equals 1. So it's just 2 equal steps. Delta x would end up being 1/2. Then it would end up being 1/2. Let's scroll down. Rewrite my derivative dy dx equals x squared minus 1/2 y. There we go. Okay, and let's use the table like usual. That's very helpful. So we first have x, and we'll have y, dy dx, and then dy. Okay, so we're starting off at h of 0 equals 2. So we've got 0, 2 there. And we need to first get dy dx. So let's plug 0, 2 into dy dx expression. Well, if we plug 0, 2 in, we would have 0 minus 1/2 times 2, which is a -1. And then as discussed earlier, the dy is just our delta x times dy dx. Let me write this. That's somewhere else. Not right there. Now we need the dy, which is just delta x times dy dx. So then the change in y, if this is our slope and we just have a delta x of 1/2, that'll then be -1/2 for that dy. And then to get the next y, we just add that change in y to our previous y value, which will then give us 3/2. And our next x value, since we're with delta x equals 1/2, is at 1/2. Our final x value is going to be at 1. Now we need that delta x, that dy dx. So we'll have 1/2 squared minus 1/2 times 3/2. Okay, well that is 1/4 minus 3/8. Okay, well, let's get a common denominator. I'm going to call that 2/8. 2/8 minus 3/8. That'll be negative 1/8. Okay, so we got negative 1/8 there, negative 1, and then times the 1/2 would mean negative 1/16 for the dy.
Mr. Hunter?
Yeah.
I think the 1/2 times the 3/2, that's 3/4 instead of 3/8.
Yeah, I don't know why I put 8. 1/2 times 3/2, that would be 3/4. Well, that makes that easier. I was just wanting to make it harder, probably. Okay, yeah, that'd just be minus 3/4. We didn't even need a common denominator there. 1/4 minus 3/4 would be negative 2/4, which is then just negative 1/2. Yeah, negative 2/4, which is negative 1/2. That fixes that problem. So negative 1/2. Then the dy, negative 1/2 times 1/2 is negative 1/4. Combine that negative 1/4 with 3/2. And we are then at 5/4. And there we go. That would be the answer. That was the goal. We wanted to approximate what h of 1 is, and there we go. We now see that h of 1 is approximately 5/4. Okay. And now Isaac asked about the BC2 on the Passwater FRQs. The BC2 on the Passwater FRQs. I went over BC1 on Friday. This is BC2. He asked about part D. I'll quickly describe how you would do a few of the other parts though. Part A. For part A, they tell you that g of x is f of x squared minus 1 times h of 2x, and you're asked to find g prime of 2. So this is just some derivative stuff here, and it would require both product rule and chain rule. This would require both product and chain rule. And it really shouldn't be that bad, that one. On B, just some basic integration. What rule do you need to, or what process do you need to use when doing part B?
Integration by parts.
Part B?
That's what I used.
Nope, not part B. Oh, wait, sorry. Nope, I was dumb. I was looking at something different. No, yeah.
No, yeah, just use sub. Never mind.
Part B is normal U sub. Part C is integration by parts.
Yeah.
Part B is just some basic U sub. Because on part B, you would define U to be h of x, which equals 2x minus 5. And you would need your du, which would be 2dx. You'd even replace your limits where u of 2 2 times 2 minus 5 is -1. Shouldn't have taken me that long to figure out. Then u of 4 would be 2 times 4 minus 5, which is 3. Yeah. And then you could just rewrite that whole thing as, since du is 2 dx, that implies that 1/2 du equals dx. Then we can say 1/2 integral from -1 to 3 of f prime of u du. And then that's definitely easy. Then integral of f prime would just be f. And then you'd just do your definite integration, f of 3 minus f of -1, and we're told it's supposed to equal 22/3, and then you can just solve from there. And then part C, as Isaac said, is supposed to be integration by part C is integration by parts. Let me put that down. Part C is integration by parts. And on part C, for the integration by parts, what should we choose for u?
H of x.
H of x? Yeah, that's right, yeah. So we would choose u to be h of x. Because we want u to be something that we could easily take the derivative of and figure out what it is. We want u to be something that that would get simpler when you take its derivative. And h of x we know is 2x minus 5, and so du is then just 2 dx because the derivative of h is 2. And we want to pick dv such that it at least doesn't get harder when you take its integral. And that we could actually work with its integral. And so if we choose dv to be f double prime of x, then v is just f prime of x, and then that will work out nicely since we have information about f prime. So that's how you will pick those for C. And I can fully go over part D though. Part D. Well, we want to evaluate integral from 1 to 2 of 6x over f prime of x times h of x. And our process on part D is going to be partial fraction decomposition. Partial fraction decomposition. Where we have the integral from 1 to 2 of 6x over f prime of x h of x dx. We want to turn that into the integral from 1 to 2 of something over f prime of x plus something over h of x. We got to figure out what those somethings are. And the way we did this originally is we looked at, okay, what is going to make f prime 0? We want to look at what is going to make this first denominator 0. And then we will cover that up and plug that into x in what we have over on the left side. So based on our graph, because our graph is f prime, since our graph is f prime, what's going to make f prime 0? Well, we got one value on the left that's not easy to figure out, one value on the far right that's not easy to figure out, but right here in the middle, we see that f prime of 4 equals 0. So when x is 4, f prime of x is 0. That's one that's easy to work with. So if we cover up f of prime of x and just plug 4 into the other pieces, that would give us, how do I want to write this? So we cover up h prime of x, plug 4 in there, and plug 4 in there. Well, h of 4 would be what? H of 4 is, 3, and 6 times 4 is 24.
24.
So we'd end up with 24 over 3, which is 8. So we got 8 right there over the f prime of x. Now we kind of do the same things with the other one. What's going to make h of x 0? What's going to make h of x 0?
5 halves.
5 halves, yeah. So we'll plug 5, we'll cover up h of x and plug 5 halves into the other x values. So h of x, this gets covered up. We plug 5 halves in here, plug 5 halves in there. Well, for the top, what is 6 times 5 halves?
$15.
Yeah, it would be, it'd be 15. And then for the bottom, that'd be f prime of 5 halves. F prime of 5 halves. Well, 5 halves is 2.5. And if we look up here, exactly at 2.5, it crosses 3. So if we have 15 on top and 3 on bottom, then that's going to end up being 5. And that's going to end up being 5. Because this is f prime of 5 halves, f prime of 5 halves, we can see from the graph, ends up being 3. And 6 times 5 halves on the top is 15. 15 over 3 gives us 5. So then we have that right there. And so then that is the integral from 1 to 2 of 8 over f prime of x plus 5 over h of x. And it can definitely be split up. What is f prime of x? It gave us, we made the integral from 1 to 2 of 8 over I'm missing something on this part. Oh, we were told that f prime of x is just a line segment. F prime of x from 1 to 6 is just a line segment. And so from 1 to 6, well, that slope we've already seen is -2. And the y-intercept would end up being a +8. Okay, So then we have 8 minus 2x must be f prime of x between 1 and 6. F prime of x, the line segment, is the equation 8 minus 2x. So we have plus the integral from 1 to 2 of 5 over h of x, which is 2x minus 5, which has dx here and dx here. And lastly, to actually take that integral, okay, the 8 would stay, divide by the dirt of the inside, natural log of the denominator, 8 minus 2x. And then plus 5 halves, natural log of 2x minus 5. Evaluated from 1 to 2. Plug your 2 in, subtract, plug your 1 in. Okay, and you should be able to finish that from there.
Well, that's why I was having the trouble at, is trying to figure out how their numbers and natural logs came in based on that plugging in.
Oh, and how you plug it in?
Right, because it seems some of the natural logs are going to be negative on the inside, right?
Yeah, but the integral of it doesn't matter that it's negative on the inside, because when you take the antiderivative, you should have natural log of the absolute value of 8 minus 2x.
Okay, got it.
So, and then the other one would be 5 halves natural log of the absolute value of 2x minus 5. So even if it ends up being negative on the inside, you have that absolute value sign there. But when we plug that first 2 in, I mean, that right there, that ends up being negative 4 when you plug that 2 in. 8 minus 2 times 2 will be natural log of 4. Plus then 5 halves. When you plug that 2 into there, that'll then be natural log of the absolute value of -1, but absolute value of -1 would just make it natural log of 1. And then you'd have minus, and then the rest of it. Since it was absolute value, if it ends up on negative on the inside, you can just flip the sign and make it not an absolute value anymore. Does that answer your question?
Yeah, I just
Okay.
forgot the absolute value there, so that works.
Yeah, we don't want to forget that the integral of 1 over u du would equal natural log of the absolute value of u. I guess since that's indefinite, I should have plus. Okay, well, that was a lot. I'll go over more questions on Friday. Any more questions that you have from these? And something that I thought could be fun for Friday. Wait, no, I'm not sure if we'll have time Friday. We'll see. I will go over the review, the humongous review sheet, section 10, Unit 10, we won't do Unit 9 since it's not on this year's exam. But I'll go over the humongous review sheet Unit 10, then answer some more free response questions. And then if we have time, I thought it could be fun to do a Kahoot, even though we're through Zoom. If you have a computer and phone, we could do a Kahoot on Friday. Okay, well, have a great day, everybody. Bye.
Bye.
Bye. Miss you guys.